Let's get started. Welcome to Theory Lunch. Today we'll have our own Ainesh Bakshi, who's going to talk about sublinear time low-rank approximation of distance matrices.
All right, great. Thanks for the intro, Rowie. So let's get started. As Rowie said, I'll be talking about sublinear time low-rank approximation of distance matrices. That's a lot of words. Let's begin by defining what that means. Okay, so low-rank approximation. Here we're given as input an n by m matrix A and an integer k. And what we want to do is find a rank k matrix X that minimizes the Frobenius norm difference between A and X. The Frobenius norm difference is basically just you take the sum of squares of every entry of the matrix, and then you take the square root. Pictorially, what this looks like is that you start off with an n by n matrix A, and you want to approximate it using a rank k matrix, which is m times n transpose, such that the inner dimension is k. And you want this product to be close to the original matrix on the Frobenius norm. And why is this useful? Well, if you see, we've gone from n times m parameters to about n plus m times k parameters. And that's something that sounds useful. Are there any questions about the problem? All right. So why do we care about low-rank approximation? Well, like I said, you can use it to compress data and compress matrices in general. And if you start with a matrix that is coming from like a real-world data set, and you want and there's some underlying structure, and you want to recover this structure, but it's been corrupted by noise, you can compute the low-rank approximation and try to recover the structure. And it has various applications to clustering, topic modeling, recommendation systems, and learning distributions. Yes?
Yeah. If I can ask an oriented question about the question actually. Is it clear that there is always a minimizer for that expression? Like is the set of rank k matrices compact or something like that?
Right. There is a minimizer for Frobenius norm, and it's unique.
Okay. But for general norms, is that always?
Right. Let's get to, I'll discuss it soon. Right. Yeah. All right. Now let's define the second part, which is a distance matrix. We begin with a point set P. This is just n distinct points in RD. And we have another point set Q. This is m distinct points in RD. And we define a metric over them. Think of this as an arbitrary metric over P Cartesian product Q. And look at the matrix A, which is basically the pairwise distances between all these set of points. And instantiation of this D would be Euclidean distance, L1 distance, L infinity, but you can pick any one you want.
Since I'm confused.
Yeah.
Since you only talk about distance to the point in P and point in Q,
right.
Triangle inequality becomes vacuous.
That's true, but we're defining P and Q generally, so Q could be equal to P, and then you'll have the same point set. Does that make sense?
No.
No. Okay, so
what does it mean to be a metric in this context?
Right. That's a bit complicated. I mean, we can take that offline. But basically, what you want to do is like you want to have a lower bound on the distances between the points at P and Q. So like you pick any distance between P and Q. And now you want to say that this is lower bounded by all other pairwise distances. They can take the sum of all the other. Okay, it's easier to think of it in the case where P is equal to Q.
Can you use that definition?
Yeah. About triangle inequality for P and Q?
Yeah, but I don't know what to do.
Right. I don't want to get into it right now because it's like, yeah.
Isn't the case that P and Q are just subsets of some space? Like
yeah, just think of that as just points in Euclidean distance for now.
Okay, fine.
Okay.
So do you mean like it should be a metric in like P union Q?
Yeah. So what I actually mean is like if you pick.
Why do you need a metric over P times Q?
There's no non-trivial triangle inequality.
No, but I'm just saying maybe this is the induced. You take a metric on P union Q.
Could define it.
About cross distances. I mean, that makes sense, right?
Yeah, that's what you do basically. You look at only cross distances and you want to.
I mean, any metric on P union Q, but you forget about distances, intra-cluster distances.
So but there is a non-trivial condition here.
It's not a condition. You just ignore that information for now. There is an underlying.
No, is there a function on pairs which is not a metric?
So there is an underlying metric, and you only care about the difference
I see.
between
You're
guys in P
saying-
and the guys in Q.
No, but I guess this question is that when you do that, you probably get any
Negative function. Or not?
That one I don't know.
Yeah, that's my question.
Okay, so I could define it. It's just, do you want to do this after the talk? Because it's like a complicated definition. It's like you look at all pairwise distances between P and Q, and you take the best lower bound on this using a two-step hop. Like.
His question is there aren't two-step hops though, because you only have distances between P and Q. Right?
Yeah, but you look at any pair of distances between Q and Q prime, right? And now you can lower bound this by looking at all distances from P to Q and P to Q prime and looking at this difference.
So also there is a triangle inequality, right? If we take three-step walks, you can't put an arbitrary metric.
Ah, yeah, three-step walks.
Yeah, you take triangle inequality for three-step walks.
Okay, fine, fine. And that's the only condition which is good.
Probably that's necessary.
Probably. Okay.
Okay. For now, just think of this as the same point set, and it's regular triangle inequality. All right, these matrices are dense, and the number of non-zero entries in this matrix is n times m. All right, so why consider distance matrices? Well, they show up everywhere in clustering, data visualization, learning manifolds, understanding and handwriting, speech and music. All right. So what makes the low-rank approximation problem tricky? Well, we have this sum of squares looking objective function. It's like minimizing least squares or something. But the tricky part here is actually the rank constraint. And the rank constraint makes this problem non-convex. In fact, optimizing over a rank constraint is tricky because the matrix rank is very brittle. What I mean by that is if you start off with this rank 1 matrix and you perturb it slightly, you might end up with a full rank matrix. So any questions about the problem? I believe Nick had a question here.
Why the optimizer exists, yeah.
Right. So that's because there's this nice term by Eckhart and Young, which basically says that you can actually find the optimal solution to this problem, to the low-rank approximation problem, in polynomial time. And let's see why that is the case. We start off with what is known as the singular value decomposition of a matrix. So we start off with this n by n matrix A, and we decompose it into a product of three matrices, U, D, and V transpose, where U has orthonormal columns, V transpose has orthonormal rows, and D is a diagonal matrix. The diagonals and entries of these matrices of this matrix D are the singular values of A, and they're usually written in descending order. The columns of the matrix U are known as the left singular values of A, and the rows of V transpose are known as the right singular values of A. I'm sure most of you have seen this before. Are there any questions so far? Okay. So how do we use the singular value decomposition to output a rank K matrix, which is what we were going for? That is an optimizer to our original problem. We do something very simple. We look at the diagonal and we truncate it to the top K by K. So the diagonal had R entries, or R was the rank. And we want to pick the top K of them. So this corresponds to zeroing out all but the leftmost K columns of U, and all but the top K rows of V transpose.
You're assuming the eigenvalues are sorted?
Yeah. Like I said, they're in descending order. And these are singular values, which is right. So this is a generalization of eigenvalues to rectangular matrices. All right, and it turns out that this rank K matrix that you get is optimal for this objective. And now coming back to the next question, it's important that this objective is actually Frobenius norm. If I replace it by any other norm, let's say L1 norm of A1 and A minus x, then this problem becomes NP hard. And it's not clear if there's a unique minimizer. All right. So this is great, but the running time of this algorithm is n times m squared, or the minimum of n times m squared and n squared times m. What this says is that if you have a really skinny matrix or a really fat matrix, you can compute the SVD really quickly. But for the case where they're roughly equal, this is a lot. And people care about this algorithm in practice, so you want something that is faster, which is the natural question to ask here. Yes?
I have a question. So what is special about Frobenius norm that this works for Frobenius but doesn't work for L1?
Yeah, it's magic, right? In fact, if you deviate from Frobenius norm just a bit. This is the sum of squares of each entry. If you take 2 minus epsilon power of each entry, it's still hard.
Partly it's because the Frobenius norm is the sum of squares, so I get like
Pythagoras theorem.
Yeah, orthonormal projections are defined in the space. And okay, any other questions? All right. So we are looking for faster algorithms for approximating this low-rank approximation problem. And what Clarkson and Woodruff showed in 2013 is that you can output a rank K matrix B such that the Frobenius norm difference between A and B is at most 1 plus epsilon times the opt. And you can do this in running time, which is the number of non-zero entries of A plus this n plus m poly K over epsilon term. Okay, so let's break this down. The n plus m term is just the dimensionality. We have an n by m matrix. The poly K over epsilon is usually a small constant. You set K and epsilon to be small constants. And n and z here is the sparsity of your input. So you can think of this as a linear time algorithm to compute a low-rank approximation for your matrix. All right, so the one thing here is that the output B, which is our actual rank K matrix, it must be in factored form. And what I mean by factored form is this n by k, k by m form that I showed earlier. And the question here is, why is that the case? Why must I write B in factored form? Tim?
If you don't, it will just be O of n m size to write down.
Exactly. So what Tim just said is that I'm claiming that the algorithm runs in the sparsity of A. Think of A as having sparsity n times m to the 0.7 or something. But the resulting rank K matrix B need not be sparse. And if I want to write the matrix B down completely, these are n squared entries, or n times m entries. And I don't have enough time to write that. So I just write it in factored form. Yes?
So is this for any matrix A?
Yes, this is for arbitrary A. Yes?
You get amplification on this? Because like testing whether or not you're close to Frobenius norm seems like it should take you a moment, right?
Right. So you can get the low rank approximation here, but you can't figure out what its cost is. Yeah. Yeah. That's another interesting open problem. Any other questions? All right. There's been a lot of subsequent work on this that it works on improving this poly K over epsilon term. Great. So the next question is this optimal? Do we really need input sparsity? Do we need to read all the entries of our matrix to compute a good low-rank approximation? And it turns out that the answer is yes. You actually do need to read all the entries of your matrix. And you can replace this 1 plus epsilon by any constant C here. And this is still true. And the reason for this is consider a matrix which is the all ones matrix, but it has one entry which is infinite. And I don't tell you where this is. So if I don't read all the entries of the matrix, I'm going to think that this matrix is just the all ones matrix. And I'm going to be really far off from my low rank approximation. Yeah?
Can you come up with like a counterexample which is sparse? Like a hard instance?
Yeah, you could just fix the sparsity pattern for the zeros in this matrix, and it's still a rank 1 matrix. And then you can hide the infinity anywhere.
Sure.
Any other questions? Okay, so like I said, finding the large entry requires reading the entire input, which is basically linear time, also known as n and z of A in this notation. So the central question that we look at in this talk is that if you know that your input is coming from this nice family, which is a distance matrix, can we get faster algorithms? Can we beat this lower bound? And it turns out that we can't. So let's just go home. Okay, so why not? So we show that that a similar result holds here. Like now you condition on A being a distance matrix, and still getting any C approximation to the low rank to opt requires reading all the entries of the matrix. And why is that? Here's the construction. So you pick the point set P to be just the standard basis vectors from 1 to n. You pick Q to be minus EI, where EI is one of these at random, one of the points in P at random. And the rest are standard basis vectors, m minus one of them. And the metric that we're looking at is L infinity. So observe that if I take any point Pi here and any point Qj here, the distance in L infinity is just going to be 1. For all pairs apart from where I pick EI and negative EI. And that one is going to be 2. L infinity is the maximum entry in your vector. Right, and like I said, it's not infinite, but I still need to find where this 2 is. Because this is a rank 2 matrix. If I want to find the best rank K or rank 2 approximation, I better find this exact matrix. And if I don't look at all the entries, I'm going to just look at, I'm going to think my matrix is the all ones matrix, and I'm not going to get a constant factor approximation. Any questions about this? Note that the rank 2 approximation gets error 0. Okay, good. Okay, but something is different here. We have a 2 there. Can we make the 2 infinite? Can I replace the 2 with infinite? The really large number. And why is that? Exactly. Which is not vacuous.
The square of all these.
Yeah. So we do have these triangle inequality constraints, and you cannot set this to be infinity. And the way to think about this is basically very simple. If I have a point set and I take a point and I put it at infinity, now the distance between this point and all the other points in P is going to be really large. So I can't just make one point really large and have all other distances to be 1. Now the other thing to note here is that if I do random sampling of this matrix, I see that it's the all ones matrix because I did not find the large entry. I get most of the matrix correctly. In fact, I get everything apart from this one large entry correctly. So this means we should be updating our notion of what it means to be an approximate solution. Okay, any questions about this?
Can you explain the last point?
Right. So if I do random sampling, I just see a bunch of 1s, right? I'm going to think that my matrix is the all ones matrix because I never saw the entry which is not 1. If I approximate this matrix by the all ones matrix, most of the entries I get correctly, right? I'm going to say there's a bunch of 1s in this matrix. All right, so this implies that we need a better notion of approximation. Okay. Now this is what we proved. This is the main result. What we prove here is that given a distance matrix A, you know that A is a distance matrix now. You can compute 2 matrices U and V such that the inner dimension is K, which means U times V is rank K, such that this is at most opt plus this additive error term, which is epsilon times the Frobenius norm of A. Note that this is different from the previous guarantee. There was a 1 plus epsilon here. That was a relative error guarantee. This is an additive error guarantee. In fact, this one is implied by the relative error guarantee, so it's strictly weaker. And the running time of this algorithm is n to the 1.001 plus m to the 1.001 times some Polyg over epsilon. So morally, this is just n plus m time. And the thing to observe here is that we do not read most of the input. The input is n times m. And we can still output a good low-rank approximation for it. Another point is that since you're only spending this much time, you're also querying at most these many entries of your matrix. And why would you care about that? Well, in some cases, computing pairwise distances between your point set could be really expensive. Like you want to compare two DNA sequences, and computing the distance between them takes a long time. So you don't want to compute all n times m of them. Here you get away with computing about a linear number of them. Yes?
Why do you need the 0.001s?
Technical reasons. Yeah. You'll see. I'll give a sketch of the algorithm. Yeah.
So to be clear, is it like a 1 plus delta for an arbitrary?
Yeah, it's a 1 plus gamma or delta for an arbitrary small constant delta. But I didn't want to introduce another parameter.
And the probability 9/10, is that?
It's just some constant, yeah.
Okay.
Yes. So, assumption is the Venkat-Freehoff assumption?
Yeah.
It's exactly that.
It's exactly that.
Okay.
To say what that is again, it's basically look at any distance between Q, the points in the set Q, right? This can be lower bounded by the difference of all pairwise distances from P to. I'll just draw it for you. Let's say this is Q1, this is Q2. I want to lower bound this distance, right? Look at all points in your point set P. It's lower bounded by the difference of all these distances. Like, just take the maximum difference between the distances from P to Q. This is morally like triangle inequality. But yeah, we can talk about it later. Yes?
Can correctness be verified quickly?
No. I mean, you can't even write the product of U times V down quickly, so you can just write it out in factored form again. Any other questions? All right, so if I have a distance matrix, yeah.
Sorry, you said it before, so it's actually a completely open question whether or not you can amplify. Like, you can't just do this a bunch or take the average. There's no way to.
I'm sorry, what?
The amplification of this, the probability, is a completely open question. You said that? Is that the case? Like,
that is
the probability of success.
Yeah.
Is there some? Okay.
Yeah. To get it with very high probability is still.
To get rid of what?
Very high probability.
Yeah, because I mean, you can probably just increase these things. Probably get linear dependence on delta, right?
All right. So this is the story so far. We started out with the singular value decomposition algorithm that ran in nm squared or n squared m time. We then saw an input sparsity algorithm where the runtime is dominated by n times m. This is just for distance matrices. Distance matrices are dense, so you have to spend n times m time here. And in this work, we get something that's almost linear in n and m. This is a summary of the results. If there are any questions about the results, ask me now, and then we'll get into the technical part. Yes?
Do you have any similar guarantees for different norms, or just Frobenius?
Just Frobenius. So it's an interesting open problem to get 1 plus epsilon guarantee. Okay, so there are some recent results that get 1 plus epsilon for general LP norms, but the running time is not polynomial. In fact, it's NP hard, so you don't expect it to be polynomial.
So you mentioned earlier that you can't, like in the previous setting, you couldn't verify if you're close to optimum.
Right.
Can you do it in your setting?
Oh, no, not at all, right? Like this is even less runtime. Like you can barely write down the factored output.
I see. So you succeed with constant probability, but you still can't tell if you succeeded.
Yeah.
Okay.
Yeah.
How big is your poly?
Yeah, that's a good question. It's pretty big. We didn't try to optimize it.
Is it more like 1,000 or like 40 or?
Let's go with 100 for now. Yeah. But I'll address that question later in the talk. Okay. Any other questions? Yes.
Somehow this should be related to Johnson-Linden Strauss. How does that compare? I forgot.
Right. So the input sparsity time algorithm uses these sketching matrices.
No, but does that mean that you can always get down to k equals log n or something like that? Or?
So k is the rank here.
Right.
It is part of the input. I give you a rank parameter as part of the input.
I
And
thought the distance matrices, a distance matrix automatically in k dimensions, I thought is roughly k, rank k as well.
right, the dimension need not be k. This could be, the points could lie in an arbitrary dimension to begin
you're
with.
approximating it with something.
You're approximating.
So suppose you were in high dimension.
Right.
To Johnson-Linden Strauss.
Okay.
And then that should be a good approximation for you, right?
Well, we're not working with the actual point set here. We're working with the pairwise distances on the point set.
No, but okay.
Distances. The
the underlying dimension and the dimension of the matrix
Yeah.
are not necessarily related.
Right. Again,
There's a theorem that says that if you take a collection of points in k dimensions, somehow the rank is k, right? So if you take points in 2D.
Distance is not Euclidean.
What?
Distance metric is not necessarily Euclidean metric.
He just has some arbitrary distances.
It's not Euclidean distance.
I understand what you guys are saying, but you don't understand what I'm saying. So I'm simply saying is I understand there's theorems that say distance matrices have low rank and low dimension.
right. So what is in low dimension? The point set?
The points.
Right. But I'm not making any assumption about the point set
I
being
don't know you are, but I just said, but if you take a bunch of points in high dimension,
right.
we know that you really only need to log n dimensions.
Well, only for Euclidean distances, right?
Okay, so I see. So you're saying for Euclidean distance, then automatically you say that the rank won't be more than k, than log n.
Right.
So k is always about log n.
Well, you could set it to be less, yeah.
The points of the matrix are, like the distances of the low rank things, like 1 plus epsilon close to what the distances of the original points are. I don't know how you could relate that into a statement about matrix rank.
Yeah, so like the...
No, but there's a theorem that says that distance matrices have low rank.
If it's the gram matrix, it is the matrix rank.
The gram matrix?
But there is a difference between gram matrix and distance matrix. I don't know if that makes a difference.
Right.
You get a matrix that pointwise approximates with rank log n. That's what Gary's saying.
Yeah.
Right? But I guess his objective is this like lowest rank approximator.
Fair enough.
Yeah, so think about the case where k is equal to 2. Your data could be in any dimension, right? Like I want to find the best rank 2 approximation to it, to the distances itself, but not to the actual point set. Yeah.
In your example, you showed basically there were only a small number of points with large difference. Here, you're just allowing the difference to be a multiple of the original matrices for Venus norm. Can you guarantee, like, I don't know, that it would be something more like the first property, that it differs by a log only on a small number of entries?
So, so like we said, like you can't get relative error, which is basically an entry-wise guarantee.
Sure.
You can get this relaxed version where you have this additive term, but that's the best you could say here. Right.
Okay, nothing better.
Yeah.
About the previous discussion,
Yeah.
you say that worst case we could still take k equals log n? Like,
No, I'm not saying this at all. Like, I'm not making any assumption about my underlying metric. It could be L infinity. And now what are you going to do?
So you might still need to take high large k.
Well, k...
You're only competing with the optimal k.
K is given to you as an input. And you want to find... You're competing with the best rank k approximation too. Yeah. Another question? Yes?
What about tangential? But if you allow bicriteria, are there other results?
Right. So that's a good question. It turns out that this lower bound,
Seems fragile, right?
this lower bound, it also holds for bicriteria up to poly k. So even if you output a poly k rank matrix, this lower bound still holds. Yeah. So the relative error guarantee is really hard in this case. But an interesting question is if you fix your metric to be something that we are more familiar with, like negative type or Euclidean distance, then you can actually get a bicriteria algorithm with relative error. But let's talk about that later.
Well, in this case, adding more rank doesn't help you unless you find unless one of
Exactly. So this lower bound, this example itself holds for. Any other questions? Yeah.
So sorry. So I mean, related to some of the questions of how this point set comes about, you're only given an interface to this metric, which you don't even know through like looking at entries of the matrix.
That's right.
So a related question would be like, okay, suppose I knew the metric. Suppose we're in Euclidean space, and suppose I told you the endpoints, and I told you the endpoints. Now you have a lot more. Not only do you have query access to the matrix, now you have a lot more information. And you still can only read off. You can read off the points and put them in time. And
right.
Anyone looked at like whether this can you could do this same problem, but now you have this additional amount of information.
Right. So the thing is, this information doesn't really help you because it suffices to compute this additive error guarantee.
No, but in terms of like, well, I guess you almost have optimal runtime because you still need to read
right.
the entries.
Right.
So I guess up to poly k factors. Okay.
Yeah. The answer to that is the extra information doesn't really help. Apart from the fact that you know that it's a Euclidean distance, in which case you can actually get this bicriteria relative error. That's a separate result.
Okay.
But for general matrices, this is the best you can do. You have to do this. You have to incur this additive error. Any other questions? Okay. Let's get into the algorithm then. All right, so no matter what algorithm I tell you about, this algorithm better be able to approximate the largest entry in my matrix. If not, my previous lower bound applies, and you can start throwing things at me if it doesn't, right? Okay, so let's make a simplifying assumption that our point sets are equal. Now we have an n by n matrix A. And the question is simple, can we estimate the largest entry in A without looking at the entire matrix? Okay, let's see how to do this. So this is our point set. Think of this as a point set P, capital P. Pick an arbitrary point in this point set. Let's call it small lowercase p. And find the furthest point from P under the metric that you're looking at. And let's call that point Q. I claim this distance is a 2 approximation to the largest distance in this point set. Does anyone see why that's the case?
Triangle inequality.
That, and yeah, Jason?
Just radius and diameter.
Exactly. So in the best case, this P that I picked would be the center of my point set. And that would give me the distance between P and Q to be the radius, which is a 2 approximation to the diameter. In other cases, you know, I'm only doing better than a 2 approximation because this distance would be larger than my radius. Okay, so what does this mean algorithmically? It means that if we read the first row, so P might as well just be the first row of our matrix, corresponding to the, like P might be the point that corresponds to the first row. We just read the first row and we look at the largest entry in this. This gives us the largest distance from P to any other point Q in our point set. And this is a 2 approximation to the largest entry in my matrix. In particular, this says that I cannot hide large entries anywhere anymore. Any questions about this? Okay. Now we need an actual starting point. So there's a beautiful theorem of Friis, Cannon, and Mambola that says if I take an arbitrary matrix A and I sample about k over epsilon rows of A according to, so I sample the ith row of A according to the L2 norm squared divided by the Frobenius norm squared. So this is the relative L2 mass of this row. And I'm sampling according to this distribution. So now you get a smaller matrix, in particular a k over epsilon times n matrix, from which I can compute another matrix U. This is a projection, this is a rank K projection, which approximates the optimal up to this additive error. There's a lot of, yeah?
Does the omega 1 depend on k and epsilon?
No. So this result actually assumes that you have an oracle that helps you sample according to this distribution. So again,
so you're sampling IID.
Yeah.
So each time I see, okay.
So let's go over this again. What this says is that you look at the ith row of A, and you sample it with the probability proportional to its L2 mass compared to the rest of the rows. And you do this k over epsilon times. You end up with a matrix S1. And from S1, you can somehow compute a good low-rank approximation. All that's important here is that it seems like estimating the L2 norm of the row is a good place to start. That's the takeaway from this slide. So the question is, if I have a distance matrix, can I estimate the L2 norm of each row without reading the whole matrix? Can I do this quickly? So that's what we're going to do. Yes?
Sorry, what is the guarantee on the S1A? So
yeah, I'm not actually giving a guarantee. The main point of this is like, it seems like estimating the row norms of your input is a good place to start. And we're going to start there and then build up from there.
Oh, sure, but whatever is the guarantee can actually guarantee you actually computing U when you have it.
Yeah, all it says is that if you decrease the dimension of your matrix, you can still recover a good low-rank approximation from it. Okay, so we're going to start with estimating the row norms of a distance matrix. All right, I'm going to describe the estimator, and then I'll give some intuition for why it's correct. The estimator is fairly simple. Like I said, you read the first row. You look at the max entry in this. You have to do that, otherwise my lower bound is true. And you set this to be eta. Think of eta as a diameter of your point set, or a constant approximation to it. Okay. The next thing that you're going to do is, for the ith row, you're going to sample b entries. B is going to be set later, uniformly at random. And you're going to take the unbiased estimator that you get from these sampled entries. So I sample b entries, let's call that set t. For all the elements in A that are sampled from this set, I look at the squared entry, or for each of them, since I'm estimating the L2 norm squared, I square everything, I scale by n over b, and I bias it by the diameter of my point set squared. Any questions about the estimator? Yes?
So here the rows have length n, is that the idea?
Yeah. This is an n by n matrix.
N by n lines, yeah.
I'll repeat what the estimator is. You sample b entries uniformly at random from each row. You look at the unbiased estimator that you get from these entries, and you bias it with the diameter squared. Yes?
It's a different p for every row, right?
Yes. Yes. This is how to estimate the ith row. Yeah. And the thing to note here is that we only access b entries of the matrix to estimate the L2 norm of the ith row. We do this for all rows. This gives us n times b accesses to the entire matrix. Yes?
So you're random sampling in every row to estimate the L2 norm.
Yep.
And this
and biasing it by the diameter.
Yeah. The diameter is giving you a bound of the variance of this estimator.
Well, let's get into that. Yeah, it's going to be important to bias it.
Okay.
We'll see why. Is the estimator clear?
Could you explain how do you do the biasing here? Like,
oh, right. So you read the first row. You look at the max entry in it. Let's call that eta. Right? Then for the ith row, you sample b entries uniformly at random. You look at the corresponding entry squared, and this is my estimator for the ith row. This is an unbiased estimator, just the way I set it up. And now I add this diameter squared term to it.
it's related to pi. Okay.
In other words, if I look at the expectation of this estimator, it's the L2 norm squared of my ith row plus the diameter. Any other questions about this? Okay. So what is the guarantee that we get? We can say that if we construct our estimator this way, then with some constant probability, we get an n over b approximation to the L2 norms of the ith row of A. And now you guys should be pretty mad at me because this is like a horrible approximation, right? Like for this to be useful, I need to set b to be really large, and I told you that my running time is n times b to create this estimator. In particular, if I want to run free Scanlan Impala, I need to set b to be omega n because I want to sample with constant probability, which basically corresponds to reading the whole matrix. That's pretty sad. So we're going to see how to use this really poor estimator to actually get a good algorithm out of it. All right, another thing to note is I could do the same thing for the columns, and I get an n over b approximation to the column norms. And what this lemma requires is basically triangle inequality. For now, the point sets are the same, so this is the normal triangle inequality that everyone is familiar with. All right, so let's give a proof sketch. This might give you some intuition for why this lemma is true. So consider the case where my point set has all distances to be roughly the same. And now I'm doing uniform sampling. And I'll get a really good estimator because let's say all my distances are d. Now I do the sampling a bunch of times, my estimator is perfect. Does everyone agree that it works in the case where all my distances are roughly the same? I don't even need the bias. Just uniform sampling works. Okay, maybe I can draw this out. I have a matrix. All the entries are 1. I want to estimate the L2 norm of this matrix, of each row of this. I can uniformly sample and my unbiased estimator will be just perfect. Good? Okay, now let's consider the case where I have one entry that's really far away. And all the other entries are again distance 1. So one entry that is really far away, let's say at infinity, all other pairwise distances are roughly 1. In this case, uniform sampling is horrible because my L2 norm is going to be dominated by the entry that's really far away. And I'm getting some uniform sample which is really small. But now the bias comes and saves us because the diameter of this point size is going to be really large and we're biasing by it.
Didn't you just oversample that column then? I mean, if you have one point that's far from everyone else, then you should be sampling that more likely than some other.
Well, we are looking at one row, right? So then one entry of this row is really large. We're estimating the L2 norm of this, right?
You do the columns also, right?
We do the columns also, but let's look at rows for now. We know that one entry in each row is going to be really large, right? And now we don't know which entry this is going to be. So if we just do uniform sampling.
One entry is far from everyone else, doesn't that sort of say that that column is large?
Yeah, there's one column that's going to be like all infinite, let's say.
Yeah, so you figured out the column that was large and now you just subsample.
How do I figure out what column is large?
You did column estimators also.
You could do column estimators too, but like how would you figure?
Those columns, all the entries are going to be large, and so your estimate's going to be big already.
Sure, but then how do I convert that into an estimate of the row norm?
Okay, no, go ahead. I'm sorry.
Yeah, the point is that I have a constant approximation to the diameter. The diameter is going to be dominated by this large entry. I'm biasing by it, so my estimate is still good, right?
You should alternate back and forth between rows and columns.
We don't want to do that. We just want to estimate row norms without looking at column norms. Okay. Any other questions? Now, the basic point of this lemma is that we can actually interpolate between these two cases. Now we get an estimator that is an N over B approximation for the L2 norms of A. Okay. Yeah.
What is instead of this eta, you add the sample from that column.
Oh, so
you require sampling from that column.
No. So eta is just reading the first row.
Yeah, but you find the column, right?
Yeah.
You know that column. Don't you require sampling from it?
I can read the first row entirely.
Yes, and you found the largest.
And found the largest entry.
And then you know that the whole column is also large.
Yes. In the extreme case where I know that one point is really far away, there's one column that's really large. But this need not always be the case.
Okay.
And basically what we show is that these are two extreme cases and we can interpolate between them and still get this approximation. Okay. So like I said, we can't really use Freeze-Curve and Impala because that would give us nothing. So what do? We have these estimates to the L2 norms and we wanted to sample the rows according to these estimates. What are the guarantees that we can get for it? All right, so we have the estimator xi, which follows this guarantee. From this, we can construct a probability distribution by just looking at the relative the relative mass of each row according to our estimator, and this is a B or N approximation. Recall Freeze-Curve and Impala required an O of 1 here. They wanted this to be a constant, so this is really bad. But okay, we'll still sample some N over B times polyk or epsilon rows of A according to this probability distribution, and we get a T by N matrix. What this looks like is you start off with your distance matrix. This is an N by N matrix. You sample the ith row with probability Pi. Pi is the L2 norm of the ith row divided by the Frobenius norm of the whole matrix. And you scale it by this square root T over Pi. You do this just to make this an unbiased estimator of the original matrix. And now you went from an N by N matrix to a T by N matrix. Okay, so that's good. But how does this help? All right. So now here we prove that if you actually construct this matrix, which we call S1A, do we call that S1A somewhere? Okay, let's just call it S1A. You want to show that it satisfies the following guarantee. So if you project away from any rank K subspace P, so P is the projection onto a rank K subspace. Look at the projection away from the subspace. It is preserved up to this additive error Frobenius norm of A. So intuitively what this is saying is that if you want to project away from a rank K space, and if you want to apply this projection for your original matrix A, you might as well apply it for S1 of A, which is a smaller matrix. And this projection would be approximately the same. So this is a complicated guarantee. It takes a bit to understand what it's saying. But the crucial part is that you're preserving the projection away from all rank K subspaces simultaneously. Essentially, this is saying, forget about your original matrix, look at the smaller matrix. The projection that you care about, which is a projection onto a rank K subspace, you can approximate it just using S1A. And you can do this for all rank K subspaces simultaneously. So this is a very strong guarantee. And it's going to be central to the rest. Yeah?
Sorry, what is S1 again?
Yeah, S1 is just sampling according to the row norms. I sampled rows of A according to the row norms. I took T samples.
So S1A is like a...
S1A is just this matrix. Yeah. Yeah.
Are you getting the Frobenius norm by like looking at all row norms together or something?
Yeah, exactly. The Frobenius norm is the sum of L2 norms of each row. So you're sampling proportional to the L2 norm of each row. Yeah.
So the statement is with probability 0.99 for all k-dimensional.
Exactly.
And not like for each fixed k-dimensional projection. No.
It's a for all guarantee, not for each. Yeah. Which is pretty strong.
Yeah.
Okay. So relative error version of this projection cost preserving sketch, we call it S1A, a projection cost preserving sketch, was originally proposed in previous work. And this required actually sampling with something called the ridge leverage scores, which are a complicated quantity and takes a long time to compute. What we show is that you can actually get this guarantee with additive error, which is weaker. But all you need is to sample according to the row norms of the matrix, which we showed is easy to do for distance matrices. Okay.
Would you just say, you said that if we go back and redo this using ridge leverage scores, you can make that work also?
No. Ridge leverage scores require you to look at the entire matrix to compute, or even approximately.
You mean in the case of where it's a metric?
Yeah, even in that case.
That's one of your things you showed?
Sorry?
Well, so you showed that at some point then?
No, you could, yeah. It's going to require you reading like the entire matrix, even if it's a metric. It's not clear how to approximate it in sublinear time.
So then you could prove that computing the ridge leverage scores or approximating them is hard? No.
Well, we don't prove that, but it's not known how to do that in constant, like in sublinear time, even getting a constant approximation to the ridge leverage scores. And what we show is that you don't really need them. You could just use this weaker, we just sample according to row norms. Okay, in the interest of time, I'm going to skip this. I'm going to skip the proof, but the corollary is important. Why do we care? Yeah.
So what's the difference between what you're doing and using ridge leverage scores? So the PCPs from ridge leverage scores?
Okay, so the PCP gives you a relative error, 1 plus epsilon.
So this is what you get.
But this is what we get. Okay. And the relative error isn't going to help you because we know that the relative error is not possible anyway because you have a lower bound. So this is actually sufficient. So we don't really care about ridge leverage scores. Okay, so why do we care about such a theorem? This projection cost preserving sketch. And the reason is the following. If I can compute an approximately good projection for the matrix S1A, then this gives me a really good solution. The same projection gives me a really good solution for A. Let's not get into the technical details here, but all this is saying is like just solve the problem on S1A. This gives you a good solution for the original matrix up to this additive error factor. Okay. So it suffices to compute a good low-rank approximation for the smaller problem, but the problem isn't that much smaller to begin with. Recall S1A is an n by b polyk over epsilon matrix times n matrix, and computing the row norms required n times b time. So after we get this smaller matrix, we can just run Clarkson-Woodruff, the input sparsity time algorithm. This is going to run in some n over b times poly, there should be an n squared. Setting b to be square root n, we can get n to the 1.5 polyk over epsilon time algorithm. This is already sublinear. But I promise something much better. And also, we don't have time for this, but note that S1A is now a smaller matrix. A rank K approximation for a smaller matrix does not even match in dimension to the original problem. So we have to recover a rank K approximation of the original matrix. The way we do that is we solve approximate regression, and you can show that you can do this quickly. But we don't have time for that. Okay, so the last part is improving this exponent from n to the 1.5 to n to the 1 plus delta.
The sketch, can you say something about its sparsity?
No. This could be a dense matrix. Yeah.
Just to be clear, AP is the low-rank approximation.
So P is one factor of the low-rank approximation. You solve a regression problem to compute the left factor. P is the right factor. It is giving you the subspace.
Okay.
Yeah, let's do it offline. We're running out of time. Yeah. Okay. Okay. So the thing to note is S1A is morally a distance matrix. I scaled some of the entries, but it still has all the distance structure that we began with. So now we can estimate the column norms of S1A really, really quickly and sample the columns to get an n over b times n over b matrix. I applied the same idea, but now to the columns. And this is going to be a column projection cost preserving sketch for S1A. So let's denote this as S1A, S2. And the estimation again takes n times b time. But now we can run the input sparsity time algorithm on a matrix that is a size n over b times n over b. Now if you optimize for b, you get an n to the 1 plus 1 over 3 poly k over epsilon time algorithm. Okay, this is better than n to the 1.5. But I promise you something even better than this. So what are we going to do? We're going to apply this algorithm recursively. At every stage, we preserve all the rank K projections into the column space and the row space. We begin with the large matrix, we sample its rows. This is a projection cost preserving sketch for the previous one. We sample its columns, then we sample the rows, and sample columns again. And we do this a bunch of times. In fact, we do this n to the gamma times, 1 over gamma times, and we get a running time which is n to the 1 plus gamma poly k over epsilon for any constant gamma. And at every level, we've preserved our row projection and our column projection. So starting from the bottom level, we can then recurse back up, solving these approximate regression problems to recover a solution for A. What is important to know here is that the reason we require this projection cost preserving sketch is that when you start at the bottom level and you're going back up, you don't know what subspace you're going to get a priori. But we preserved all of them. So no matter what it is, we can still recover a good low-rank solution for the next step. Yeah, that's a lot. Yeah.
Does your poly depend on this delta or whatever?
Gamma? Yeah. The poly k over epsilon term doesn't, but I'm hiding the gamma factors here. Let's just say gamma is an arbitrary small constant, so I don't have to worry about it in my big.
There's like a 2 to the gamma running around or something.
It's not 2, it's like a polynomial in gamma, but yeah. Okay. So finally, I made a big deal of getting really fast algorithms. Does it actually help in practice? So if you take a 10,000 by 10,000 matrix and you run SVD on it, it takes forever. If you run an input sparsity time algorithm on it, it's significantly faster. And then if you run our algorithm on it, it's really, really fast.
What's the scale? What are we looking at?
So this is a 10,000 by 10,000 matrix.
What's K? What are the numbers?
K is 40.
What are the units? What are the units?
This is time in seconds. Yes.
Draw a graph.
Here's a graph. Okay, so the blue part here is the optimal error. This is what SVD achieves. The red bar is what our algorithm achieves, and the orange one is what an input sparsity time algorithm achieves. So if you're doing SVD,
what's the input?
The input is a distance matrix.
Which?
Any distance matrix. Over here, over here it's an MNIST data set. Over here, this is an MNIST data set. It's a popular machine learning data set. It doesn't really matter.
What's the distance?
What's the distance?
Yeah, so this is for Euclidean distance.
Oh, like pixel distance.
Euclidean distance between two pictures.
So that's like embedded in like pixel space, or
MNIST is binary, isn't it?
It could be whatever, right? I can still compute the Euclidean distance. How does anyway? The point is, if you're computing SVD, you might as well just run this algorithm, and it's a lot faster. And by a lot, I mean a lot. Okay. So what are some open questions? One question is, can you improve the sample complexity and running time in terms of n and m? I gave an n to the 1 plus delta running time. Can you improve it just to an n? And there is some very recent work by Indek et al. that actually does this. Musco and Woodruff showed in Fox 17 that there is a sublinear time low-rank approximation algorithm for PST matrices, which is another interesting family of matrices. Are there any other families of matrices for which we can do this, which have some structure? This is something that I mentioned before to Venkat, that if you have special matrices, like you know that your distance is Euclidean or negative type, can you get relative error guarantees? And it turns out that we have some work that gets a bicriteria relative error guarantee for these metrics. So we saw that we can approximate the L infinity norm of a distance matrix by just reading the first row up to a constant. Can we estimate other norms of distance matrices in sublinear time? And what else can we do quickly with distance matrices? All right, thanks. Right, questions? Yes?
Sorry, what's the negative type matrix?
Yeah, it's Euclidean distance squared.
Ah.
Yeah.
So I'm still a little confused that you took like a bad estimate of the row norm to get a good estimate of the low rank approximation.
Right.
My understanding is you have a bad estimate of this.
Yes.
This is causing you to like possibly oversample rows.
Yeah, by an n over b factor, right?
I see, compared to if you had the actual row.
Exactly. And now I've decreased the dimensionality of my matrix from n to, let's say b is just the n to the 0.1. So from n, I've gone to n to the 0.9 times n to the 0.9 matrix. This is like only slightly smaller.
So the
but if I recurse like a bunch of times, in fact, 1 over the factor that I'm off by, 10 times, then I'm getting a matrix that's independent of the dimension.
So the badness of estimating your row norm,
Yeah.
Basically accounts for how many recursive steps.
Exactly, exactly. Yeah.
So why do you need to set b to be polynomial, and then why don't you set it to be like log, or like, I mean, you're just gonna like if it's 2, you recurse log n times.
Right.
But then you don't get a so you can't do that.
The reason is that this blows up as I do my recursion.
What blows up?
The error blows up. The additive error is epsilon times the Frobenius norm every time.
Yeah, but just set epsilon to be 1 over polylog. Because that's a lot. Would that work? No, right? Because otherwise you would have done it.
Yeah. There are some technical issues. Like there are a bunch of stuff that I didn't describe, like approximate regression that takes longer when you. Yeah. Okay. Yeah, Rory.
Somehow you have control over the failure probability of like PCPs.
Yeah.
Because otherwise you can't just repeat this.
Yeah, you have control over it up to a constant. Like you can push it up by Marcos to an arbitrary constant probability. So and then you're just doing this a constant number of times because you can't unit bound over anything more than a constant. Yeah.
So like there's this like outstanding pursuit in like the function analysis community about like characterizing which spaces admit dimension reduction.
Right.
And I know there's a variant of the question where you're allowed to have error in terms of the average distance.
Right.
Which I think corresponds to the L1 version of your question.
It does.
Do you happen to know, like, in the L2 version, which is your question exactly, like, is there, like, some magical fact that, like, all spaces, like, all metrics admit dimension reduction, or, like, something much wider than what's known for the, like,
well, if your notion of distortion is the one that I told you about, then yes. But if it's not, then I don't know.
Okay.
Yeah. Jason, you had a question?
No.
Okay.
Well, my question was, suppose you have this matrix, how do you sample entries from that? But I assume this is regression.
Oh, no. So if you have an n, you do the uniform sampling again. You just compute the estimates of the row norms again because this is a distance matrix.
But how do you like query points from that?
Oh, I know what rows and columns to sample, right? I in my previous step, I figured out what subset of rows of my original matrix to sample, right? And now I can just go query the original matrix on that location.
Because what I mean is that this MIB matrix by MIB, it has too many entries to even store.
Yeah. You don't need to explicitly store them. You just need to keep the mapping to go back and query the original matrix. Yeah.
Any more questions?
Okay.